Hello, my name is Flaminio, and I present the work Polyurethane Tensile Tests, Conventional and Digital Image Correlation Analysis. It was done in collaboration with Ronaldo Ariati, Verônica Noronha, Romeu Costa, and João Ribeiro. So first I will present a brief introduction, after which I will talk about the methodology, results, and our conclusions. Polyurethane is considered a versatile polymer for many reasons. For instance, it has wide applications as paint, coating, foam, adhesive, and even in biomedical devices. It can be a thermoset or a thermoplastic polymer, and it can be obtained from petrochemical or natural sources. Its main characteristics are low cost, high elasticity and resistance in tensile and impact tests. It has good abrasion and corrosion resistance. And also it can be combined with reinforcements, as in a composite, and these reinforcements can be fibers or particles. To determine some of the mechanical properties of these materials, the tensile test is the most used due to its great ease of application and the flexibility of the method. However, conventional methods such as the use of strain gauge data or crosshead motion displacement may not provide detailed information about the strain field or be unable to calculate the material's Poisson ratio. Thus, digital image correlation methods are a promising alternative. This is a method that measures the strain field without contact with the specimen surface. And this measure is done by tracking of previously painted points on the specimen surface, and these points are registered by a camera during the test and processed by a software. It has high sensitivity and can acquire strain data in several planes and axes, so the longitudinal and transverse strain can be measured and used to calculate the Poisson ratio. Another analysis is the scanning electron microscopy that provides us images that reveals bubbles and the interface between reinforcements and the matrix. This way, our study carried out the tensile characterization of two polyurethane resins, one petrochemical and one natural. And during this process, we used also the digital image correlation and the scanning electron microscopy. About the methodology, samples were manufactured using bicomponent polyurethane resins, which means after mixing two reagents, a polyol and an isocyanate, the polymerization reaction starts. In our work, we used polyurethane from two different sources and made by two different manufacturers. The first one was a green polyurethane from a castor oil natural source made by Cal, and that should be mixed in an equal 1:1 ratio. The second one was manufactured by Sika. It was a petrochemical polyurethane, and it should be mixed in a mass ratio of 100:19. For the Cal polyurethane, first we mixed the polyol with calcium carbonate, that is a particulate material that can be used as a reinforce. And the amount of calcium carbonate inserted was enough to provide the 20 or 30% of the final weight in the specimens. From the 20% samples were done 2 batches, and at the second batch, some small improvements were applied, as increasing mixing time and heating the polyol at 50 degrees for the calcium carbonate mix. And after these two reagents mix, bubbles were removed in a vacuum chamber. It was a degas process, and the resin was poured inside the molds. During this, inside one of the Sika samples, e-glass fibers were positioned and represented 15% of the final weight. To ensure the flatness of the specimen surface, above the completed filled mold, a plastic cover, an acrylic plate, and a metallic piece were placed. And finally, the curing was done at 50 degrees, and the samples were only removed from the mold after 12 hours. The tensile tests were carried out according ASTM D638 4 different samples were analyzed, each one with 5 dumbbell-shaped specimens, and also images were taken during the test. One picture was taken each 5 seconds and analyzed using Google Correlate software to give us the longitudinal and transverse deformation used to calculate the position ratio. And this image analysis was the digital image correlation. And also we used a scanning microscopy, and it was done in a Phenom Pro desktop scanning. For all the tests, the highest results were obtained for samples with Sika resin and fiberglass reinforcement, reaching a tensile strength of around 117 megapascal. Sika samples from the unreinforced group presented a maximum tensile value around 11 megapascal, a value that was consistent with the manufacturer's datasheet, which informs 13 megapascal with elongation at break of 80%. And these values from the pure Sika polyurethane are lower than those obtained in all KEL samples. And about that KEL materials, compared to pure resin, which according to the literature has a tensile strength of 20 megapascal, the particles also acted as a reinforcement, and it is noted an increase in the strength. The samples with 20% of calcium carbonate had average values of 29 and 32 megapascal, a small increase due to the better homogenization on the second batch, which reduced the effects of calcium carbonate as a stress raiser in the composite. In samples with 30% of calcium carbonate, the maximum tensile reached was 37 megapascal. Even though it worked as the calcium carbonate worked as a reinforcement, as these particles were only mixed with the polyol, using large amounts of calcium carbonate made the homogenization difficult, justifying this big standard deviation that you can see. About the Poisson ratio, the literature presents values for pure polyurethane around 0.44. Also, in a composite presented in the literature with 7 unidirectional cotton fiber layers, the coefficient was reduced to 0.317. Similarly, in the present work, the addition of fibers reduced the transverse deformation of the specimen, which also reduced the Poisson ratio from the pure to the reinforced sample. And all the values obtained were consistent with the literature data and were between 0.428 and 0.44. About the scanning electron microscopy, images were analyzed revealing a high number of bubbles on Sika's polymer, which contributes to the reduction of the maximum supported stresses. The pores, that has dimensions up to 25 micrometers, were at the regions where the cracks started during the tensile tests, and had the breakage. As the presence of these regions with pores was not uniform all over the tested samples, the results deviations presented are justified. Our conclusions were: first, tensile strength results were close to those presented by the manufacturer, with fibers and particles acting as reinforcements. Digital image correlation proved to be an efficient method to obtain Poisson ratio, and in future works it can be used also to obtain all the stress and strain curve. And finally, bubbles or voids had a great impact on the tensile test results of Sika per samples, which may have contributed to the standard deviation presented on the tensile strength that was around 17% of the value of the maximum stress value obtained. That were our references, and thank you for your attention.